Oh, hey, what's up, everybody? You are about to witness my very first YouTube video ever. So, I've never done this before. Hopefully, it turns out. Hopefully, the volume and all that sort of thing works out. If not, then we'll try something else another day. But anyway, let's do this. Characteristics of polynomial functions. Here we go. So, first off, one thing I want to say is that when we get to the end of the polynomial unit, basically the end goal is whenever given any sort of polynomial function, we should be able to sketch the graph. We're not there yet. We have done no graphing at all. All we've done so far is factoring. So speaking of which, if we're looking at this question right here, and it's asking which of these functions are polynomial functions, well, first of all, before I give an actual definition or anything, let me just say that all of the all the factoring sheets that you guys have done over the last few days, all the different factoring techniques and everything, all those functions were polynomial functions or expressions. So you already kind of know what polynomials look like. And if you're looking here at these 5 equations here, you'll probably notice that this first one is a polynomial. But why? All right, well, check this out. The official definition of polynomial functions would say that you have to have x, or whatever variable we have, to the power of a positive whole number exponent. So if you look at this first one, there is no exponent next to the 3x. So that means there's an exponent of 1, which is a positive whole number. Then you see x to the 2. And then you see no x at all in the third term. So this is a polynomial function. So is the second one. Okay, you see positive whole number exponents of 4, 3, and 1. Now you might say to yourself, oh, what about this fraction right here? That's a fraction. That's not a positive whole number. But that's also not an exponent. Okay, you can have fractions for the coefficients, the big numbers in your equation. You just can't have fractions for the exponents. And you certainly cannot have trigonometric functions. This is not a polynomial function. Okay, so we cannot have sine, cosine, tan, any of those types of functions. That is not polynomial. That is a trigonometric function. So we'll say no to that one. Also, if we take a look at the fourth equation listed here, that's also not a polynomial function. And the reason for this, as you may or may not remember from grade 10, the square root of x is equivalent to x to the power of 1 over 2, which is definitely a fraction. So we would say no to this one as well. And by the way, if you don't remember this, this is something that's going to come up in Miss Johnson's 12A class in probably another few weeks. And then finally, we look at the last function that's listed here, and we have a negative 2 as an exponent. So we cannot have negative exponents, so this one is not a polynomial function, just the first two. Okay, let's check this out. We have some more terminology here. So we have a polynomial function written here on the top of the page. As you can see, we have exponents of 2, 4, and 1. All of those exponents are positive whole number exponents. This is definitely a polynomial function. The first thing that's asked here is to write in descending order. Well, descending means that you're decreasing in value. So what you want to do right here is you want to write the terms of the polynomial function in a different order. So you definitely want to start off with the largest exponent. So this is going to be the term 7x to the 4. There's no x to the 3 here, so we can leave that out. But we can go to the next highest exponent. This will be 3x to the power of 2. Then we go minus 2x. And then finally, the term with no x at all, which is the plus 1. And that is the same polynomial function, but this time it is written in descending order. Okay, so why would we write things in descending order? Well, first of all, you probably noticed that all of the polynomials that you have been asked to factor up to this point have been written in descending order as well. And also, it makes it easier to find these little bits and pieces of information that we're going to get to right now. We're asked to find the degree of this polynomial. The degree of any polynomial is equal to the value of the highest exponent, which in this case is 4. This is a degree 4 polynomial. And of course, if your polynomial function is written in descending order, it's going to show up as the first term. Also, related to that, at the very bottom here, we're asked for the maximum number of x-intercepts. That's also equal to 4. The degree of your function is equivalent to the maximum possible number of x-intercepts. So, of course, that's one clue of what the graph would look like. We have no idea what the graph of this function looks like at this point in time, but we do know that there's a maximum of 4 x-intercepts. Next up, okay, we're going to go back to part B here. It says leading coefficient. Okay, so the leading coefficient here is positive 7. So leading is when it's in descending order. You can just look at the first term. And of course, coefficients are the big numbers that are in front of the x's. So if it is in descending order, then you can look at the first term and you can see that the leading coefficient here is a positive 7. Next up, we're asked for what is called the constant term. Constant term is a term with no variable. And once again, if you have this written in descending order, it will appear last. So in this case, it is a positive 1. Also, the constant term and the y-intercept value are also related. They're always the same. However, because it's a y-intercept, I'm going to express it as a coordinate point. And for all y-intercepts, your x value is 0. So once again, okay, we don't know very much about this graph at all. We will in a couple of weeks. But right now, what we do know is that there's a maximum of 4 x-intercepts. And we know what the y-intercept is. It's 0, 1. Okay, let's take a look at this right here. This is some more terminology. This is basically just asking, given a degree of a polynomial, we can classify it as being linear if it's degree 1, quadratic if it's degree 2, and of course you have studied those in grade 10 and 11, linear and quadratic equations. We're focusing more on degrees 3 through 5 in this section. This is the grade 12 math, cubic, quartic, and quintic polynomials. Okay, so we're going to take a break from the whiteboard here for a second. You don't really have to write this down, what I'm going to show you, but it's probably a good idea to just kind of observe. I believe in English class, they refer to this as foreshadowing. So like I said, okay, the end result of this unit that we're doing is in the very end, you should be able to sketch a graph of a polynomial function. So what I'm using right here is the Desmos.com app or web-based service. It's a graphing program, strongly recommended. If you look at the very left here, you see 5 different polynomial functions, all in descending order, and they go degree 1 through degree 5. Let's just take a look at what each of these graphs look like, one at a time. Again, you have no idea how to graph these. The only thing you would know really is the y-intercept. So you can take a look at this first one. This is a linear equation, degree 1. You can notice that the degree number, which is 1, matches up to the number of x-intercepts. And it also matches up to the number of directions that the graph goes in. This one just goes up. That's just one direction. Shout out to One Direction. All right, let's take a look at this one right here. This is an x to the power of 2 graph. This is a degree 2 function. And you can see that the degree number is equal to the number of x-intercepts. You can also see that the graph goes in 2 different directions. Starting from the left and moving right, you can see that this graph goes down and then up. So 2 x-intercepts, 2 different directions or waves. And then also remember the constant term, which is a -3 in the equation, that's equivalent to the y-intercept, which is -3. Okay, let's look at a degree 3 function. You can see right here, a degree 3 function, it goes up, down, up. As you move from left to right, you can see it go up, down, and up. 3 different directions or waves. We have 3 x-intercepts. And we have a y-intercept, which is a constant term, which is equal to -2. Then moving on to degree 4, you can kind of predict what's going to happen here at this point. You can see that this graph goes down, up, down, up. That's 4 directions. It's a degree 4 function. And lastly, degree 5, you can see that there are 5 waves here. Up, down, up, down, up. 5 x-intercepts. And you can see that this graph right here is definitely a degree 5 function. So again, okay, I went through that pretty quickly, but you don't have to copy anything down. We're going to get to graphing in another week or two. In the meantime, all right, what we're going to do right about now is we're going to take a look at one last thing, which is called end behavior. So end behavior is basically a term that's used to describe in what quadrants does the graph start and end in. So once again, okay, you read graphs like you read an English sentence. You move from left to right. So you can see up here in the upper right corner, I just have marked the 4 quadrants in the XY plane. It starts in the upper right corner as quadrant 1, and then the quadrants move in a counterclockwise direction. So if you look on the left, you see quadrants 2 and 3. You look on the right, you see quadrants 1 and 4. So when you're reading a graph, every graph will start in either quadrants 2 or 3, and every graph will end in quadrants 1 or 4. So I've broken them up into even and odd degrees. So you can see the top 2 graphs that I have here are positive even degrees, a positive x squared, and a positive x to the 4. You can see with those ones, they begin in quadrant 2 and they end in quadrant 1, and that is the end behavior. You can use symbols and quadrant numbers. You don't have to write out in words. And then similarly, okay, if you look at the negative even ones, negative x squared, negative x to the 4, you can see that they begin on the left in quadrant 3 and end in quadrant 4. You definitely want to keep this handy for the next couple of weeks. We're going to keep coming back to these end behaviors. Those are the even degrees. We also have odd degrees. So the positive x3, positive x5, they begin in quadrant 3 and end in quadrant 1. And similarly, the negative odd ones, negative x to the 3, negative x to the 5, begin in quadrant 2 and end in quadrant 4. So once again, okay, you want to get all that stuff down. Okay, you're never going to be asked for any definitions or things like that, but you definitely want to know what these terms mean. You hear the words constant term and degree, and you're reading a question. You need to know what the question is asking for. So that's what that's all about. I want you guys to take a look at page 114, numbers 1, 2, and 4. Those are questions that will help you wrap your head around all this new terminology. All right, thank you, and until next time, hit that subscribe button.